is certainly on there. And then this topic is our last thing that we're going to cover that will be on this upcoming exam. So cables subject to discrete load. So this is our last topic for that upcoming exam. The exam is on April 20th. So Tuesday, April 20th. Actually, our exam, that was not my original date for the exam, because I saw when they published all the exams that a lot of people, and I asked the registrar how many, it was going to be like 80 people would have had like 4 exams. And that would have been originally scheduled for next week. They would have had 4 exams, like Monday, Tuesday, Wednesday, Thursday exams. And I was like, hang on, let's move that. So I asked the registrar, can we move it to the following week? Not ideal either, because it's after E-days, but certainly better, I think, than having 4 exams all 4 days in a row. Okay, so our cable subject to discrete loads. Our learning objectives, what we need to be able to do, what we're responsible for, is to draw an FBD of any joint, any segment, and the whole cable system. And actually, this is all of our potential FBDs. We're going to approach these the same way we've been talking about FBDs recently, which is complete enumeration. So we need to be able to identify all of our FBDs and then pick the correct FBD. We'll do that by just saying, I want an FBD with knowns and not too many unknowns. So a lot of similar procedures and similar concepts and ideas that we have done in the past, just for a slightly different system that has cables now. Explain the relationship between slope and maximum tension. This is the same as it was before. Maximum tension will occur where there's the maximum slope. So wherever is the steepest slope, that's where we're going to have the maximum. We'll write that down. And then there's also this relationship that we want to identify. And it's the basically Pythagorean theorem, and we'll talk about that as well. Our homework problems. First one, there's this video solution. You don't have to watch the video, but it can be helpful. And then you're asked a multiple choice question for that discretely loaded cable right there. Here's a better picture of the types of problems that we're looking at here. On this one, we have multiple segments of this cable. You can see each one has a unique slope. And in between all the loads that are applied to this thing, we have supports at A and E. And so they're asking us to find some of the geometry, determine the sag at B and the sag at D. We also need to find stuff like maximum tension in our cable and the tension in each segment. Problem number 3, we're asked to determine P, the sag at B, and the maximum tension. You can see these point loads, these discrete loads in between each cable segment. So we'll jump into this example here, but before we get into that example, let's write down a few key things, which some of them we've talked about already, the things that we want to write down. So the one of those for cables, and let's finish our cables subject to discrete loads. And we'll draw the picture that's off to the right there here in a second. So cable subject to discrete loads. Well, one of the things is the weight of the cable is neglected. And it's a fair assumption, It's a fair assumption to do that because the weight of the cables is typically really small compared to the loads that are applied to it. We have all 2 force elements. Right now that we're back in cables, all of these are 2 force members. So we know the line of action goes along each of those segments of the cable. The max tensions occur in the segment with the steepest slope. So if we can figure out which one has the steepest slope, that is going to be where our maximum tension occurs. Also, our steepest slope can never occur at an interior segment. it'll always be a segment against the supports there. So in this one, it'd either be AB or DC. And then we talked about in our learning objectives, the 3 types of FBDs. And so those 3 types of FBDs include, we could do an FBD at a joint. And so that would be just like joint B, just like we did with trusses. When we do that, we only have 2 equations of equilibrium, sum of forces in the X and sum of forces in the Y. So that means we can only solve FBDs that have 2 unknowns. If we do a segment, which is like with trusses, when we cut the left side, or we cut through the middle of the truss and we looked at FBD to the left or an FBD to the right. So we could do a segment, and we'll look at all these, we'll use all these different types of FBDs in our examples today. And then the last one is the FBD of the whole thing. And so these 2, we have sum of forces in the X for both segments and the whole, sum of forces in the Y, and we have sum of moments equal to 0. So for those, for segments in the whole, we can do FBDs. We can have FBDs that have 3 unknowns, not just 2 unknowns like for joints. I'm going to move that over here so we can continue seeing that. And then let me move this over there. Okay, so let's go ahead, and I put this picture on here just so we have this nice picture. We can really visualize what is going on here. But let's go ahead and let's rewrite this as well. Let's draw our given information, and so we have point A, and just like we've done before on some of our problems, it's nice to do the points first, and then we can draw the cables in between. Point B maybe is about right here. Point C. Is maybe about right there. It's definitely below B. And then point D, we want to make sure that it's not above point A. So we can just put it right there. And then it doesn't have to be perfect, but it's nice when the locations are at least relative in the same spots as the original. And then we have these supports up here. They kind of look like pins, but if you think about this, these are cables. And so even if we do have a pin, we know that the line of action still has to go along the length of those cables. We have a couple of forces here that are known. We have 50 pounds right here, and we have a 100 pounds that's right here. We have some geometry as well, like they tell us that the horizontal distance between each of those there is, we have a 4 foot, and then we have a 5 foot, and then our last one there is a 3 foot horizontal distance. Vertical distances, they give us a couple of vertical distances. They tell us this on the left side over here, that's a vertical distance of 7 feet. And then they also tell us the vertical distance between the 2 supports, which is equal to 4 feet right there. So I think besides our labels on our points, which we will add now, that is all the given information, A, B, C, and D. They're asking us to find, for this problem, T max and YC. They technically do not give us this distance down to point C. they need to tell us, and this would be in our given information, that YC is really the distance from, and actually let's call it A to C. How about, instead of calling it just YC, be a little bit more descriptive. So down here in the find stuff, I'm going to also change that Y from A to C is what they're asking us to find. So Tmax and that distance from A to C, which would be called like the sag in the cable at that specific location. So for our solution, really what we want to do is, to solve this thing, we want to pick an FBD with knowns and not too many unknowns. Just like we've talked about before with cables. And so how do we do that? Well, it's back to the complete enumeration of, we could do an FBD of this, we can do an FBD of that, we can do, and so identifying, right, we first need to identify all of our possible FBDs. Well, let's start with joints. You know, what if we did an FBD at joint B? And one of the things to pay attention to in cables is whether or not we know the slope of the cable. In this one, we only have one that has a known slope. This A to B has a known slope in our given information. B to C does not have a known slope because we don't know why A to C. C to D also does not have a known slope because we don't know the vertical distance from B to C. We don't know the vertical distance from D to C. So this is our only known slope, is from A to B right there. So if we cut through, if we did an FBD at B, for example, let's just think about this. We're not going to draw it, but we'd have AB as an unknown. We would have B to C, the tension in B to C is an unknown. And we would also have theta from B to C. So the angle of B to C would be unknown. We'd have 3 unknowns. Well, that's too many. We'd find the same thing at C. We would find the same thing at D. Actually, we don't have any known values. Remember, we want to pick an FBD that has knowns. Those knowns are super key. Well, a lot of times in cables, that known slope is really good to cut through because it's kind of like you know, picking an FBD with a force, with a known force, is picking an FBD with a known slope. So what if we did cut through that one? If we cut through B and C, and then how do we include knowns? Well, let's include the 50. Let's include the 100. And just like with trusses, when we made a cut and we were doing segments, we typically always go all the way to the right, or we go all the way to the left. And in this one, I went to the right because that's where my knowns are. This will work for our FBD, and let's draw that and talk about why. So FBD of B, C, D is where we are going to start, but we really found it by complete enumeration, just looking at all of our possible choices. So let's draw a point. Here's point B, there's point C, and point D is about right here maybe. So we didn't cut through this segment of the cable right here. This is an internal force because we didn't cut through that segment. We didn't cut through that segment right there. We have our applied loads. We have a 50 pounds that's going right there. We have a 100 pounds that's right there. We have our tension in A to B, and that tension in A to B, we're showing it first, it's a pulling force because in cables, not only they're all 2 force members, but cable always has to be in tension. So we don't have to worry about whether it's in tension or compression. We know it's always going to be in tension. And we also know the slope of this. We know that this is this is a 7, that's a 4. And so then this would be You do the calculation, that's an 8.06 feet right there would be the hypotenuse. So we know the slope of that one right there. Now over here at D, because we don't know the slope of C to D, and I always like to do the supports as an X and a Y. So I'm going to call this a DX. Again, it's going away from point D, so it's in tension, and a DY going away from point D right there. And so we're doing this because we don't know the slope of DC, right? So we're going to do this as a DX and a dy right there. Now we do know some other distances though, like we know that this distance right here is equal to 5 feet. The horizontal distance there is equal to 3 feet. And we also know the vertical distance between point D and B, because we know where B is relative to A and we know where D is relative to A. And so that's going to be 3 feet, which is 7 minus 4 equals 3 is how we're doing that one right there. Let's also add all of the joint labels here. A, or no, that's not A, that's B. So this is point B, this is point C, and that's point D up there. So now let's think about why we picked this FBD. When we're going through our complete enumeration, well, we cut through a known slope because we don't, that's like a known force. And so utilizing that known slope is beneficial for us. And then let's look at how many unknowns we have. We have TAB, we have a DX and a DY. So we have 3 unknowns, which is fine because we have 3 equations. So that's good that there's only 3 unknowns. If we had cut through another segment, say we cut through B to C instead, well, that would have 4 unknowns because the slope of B to C is unknown. So this is actually, if we started going through and looking at everything, this is our only FBD for this particular problem that only has 3 unknowns. Okay, so now that we have an FBD with 3 unknowns, we can start to solve for our unknowns. Using the moment equation is just a nice place to start because we can get rid of unknowns. Like how about the moment about D is equal to 0? We have our counterclockwise positive sign convention. Let's see, that moment about D, we'll have our 50 pounds is going to be positive, and that's times the distance of 8 feet. We're going to have our 100 pounds, and that's also positive. That's times the distance of 3 feet. And then we're going to have our TAB will break into the X and Y components. So the Y component would be 7 over 8.06 times TAB. And that is going to be multiplied times, let's see if that's the, that's the Y component. We could draw it on here. I'll draw it in purple, right? There's the Y component going up. We have the X component going horizontally. The Y component with the vertical component right there, how far is it from point D? It's 8 feet. So times 8 feet. And then we look, is it negative or positive? It's actually going to cause a negative rotation about point D. So we have a negative there. And then how about our X component, 4 over 8.06 times TAB? That's going to be times that 3-foot vertical distance. And we look at that one, and is that causing, if we think about this line of action going here, what direction is that causing? That's also causing a counterclockwise or clockwise, so that's going to be negative as well, because that's going to cause a rotation going clockwise about point D. Set all this equal to 0. We can solve for TAB, and we're going to find that TAB is equal to 82.94 pounds. So then we just solve for our first tension in that segment, A to B right there. We can also solve for dx and dy. Sum of force in the x is equal to 0. We would find that dx is equal to a 41.2 pounds. And then sum of force in the y is equal to 0. We're going to find that dy is equal to a 77.93 pounds. So we just solved for all those unknowns in that particular FBD. But what are they asking us to find? They're asking us to find that YAC, and they're also asking us to find the maximum tension. Well, is AB, the maximum tension is 82.94? Is that our maximum tension in our cable? Well, if it's the steepest one, it is, but we don't know what the slope of C to D is, do we? So we need to find what's going on right there at C to D. Let's look at another FBD to look at closer at C to D. This would be an FBD of a joint. How about the FBD at D? Because now we know dx and dy. And so if we did an FBD at D, well, we've got this known dx here, which is 77 point, oh no, that's dy. So dx is 41.2. We know that dy is equal to 77.93. And then wouldn't we have a tension from D to C? Also an unknown theta from C to D. Well, we've got two unknowns, which is totally fine. We can solve for those two unknowns, but we also can find TDC based on dx and dy directly. And so this is not an equilibrium. This is really more of a geometry thing, that TDC is going to be dx squared plus dy squared. And so this is really a geometry equation, not an equilibrium equation. But isn't TDC going to have the same line of action of dx and dy? And so if it has the same line of action, then the components of TDC are going to be exactly the same as dx and dy. So we can solve that TDC. We don't even know that the geometry is yet. And actually, this is easier than doing equilibrium. Using this is easier than doing the equilibrium, because in equilibrium, we would have an unknown theta, right? We'd have an unknown theta in that equilibrium equation. Well, TDC is going to be, for this problem here, is going to be 88.15 pounds. Oh, sorry, and I just saw the chat there. How did we find dx and dy? We found dx and dy by summing. I didn't write out the equations, but I just said we could do it by summing forces in the x and summing forces in the y is how we would solve for those. But I didn't explicitly write out the equation, but you just take all the forces in the x, set them equal to 0, solve for dx, sum all the forces in the y. There'd only be one unknown in both of those equations. Okay, so we just found TDC. Now we know the steepest slope is going to be at the end points, right? So steepest slope is always in the end segments. It can never be in the middle. It's physically impossible for it to be in the middle, because when you put a load somewhere, it pulls the rope down such that the steepest slope will always be at those end segments. So then we know all we have to do is compare TAB and TDC. So that means that this one is the maximum. So our T max is TDC by just comparing with our TAB over here. We could use this FBD to find theta, but let's look at another FBD to find theta, to find our geometry. Okay, so we could use the FBD at D to find theta, and then use theta CD to find the y from D to C. But let's look at another option. Will be the FBD of C to D. So if we take C to D here, we have our known dx of 41.2, a dy of 77.93, our segment there from C to D. We will have this unknown tension from B to C. All right, I'm taking the FBD of C to D. Zoom out over here and look, I'm basically doing this FBD in red right there. So C to D, so I'm cutting through that B to C. And that's where we get that tension from B to C. We'd have our 100 pounds right there. And we have this unknown distance here from C to D. We have a known horizontal distance from C to D is equal to 3 feet. We also would have an unknown theta from B to C. Any questions? Right, yeah, how can we find that y C to D? We could do, well, if we did the moment at D, how many unknowns would we have? I see a Olive in the chat there is saying moment at D, and we could find TBC. Well, we would have, actually, wouldn't we have 3 unknowns? We would have TBC, we'd have theta BC, and we would have or YCD. We would have 3 unknowns if we did the sum of the moments about D. D actually is where we know stuff, right? We know dy, we know dx. So yeah, moment about C, right? And so if we did the moment about C down here, we could find actually YCD is going to be our only unknown. So if we take the moment about C, we're going to have a dy times 3 feet, and that's going to be positive. we're going to have a negative dx times y c to d is equal to 0. And if I rearrange this so that I get my forces on one side, so dy over dx, and my distances on the other side, we're going to end up with an equation that shows that the ratio of the forces is equal to the ratio of the distances. Right? So it's saying that the dy over dx is equal to the vertical distance. So the vertical force over the horizontal force is equal to the vertical distance over the horizontal distance. So this can always be applied at the supports. So if you know your ratio of your distances, or if you know the ratio of your forces, you can use those ratios to find the other one, which comes just from an FBD. And that's why I wanted to show you this other option of C to D. And like I said before, though, we could have done theta CD from this. We could have done theta CD from this FBD over here, the FBD at D, and found exactly the same thing. So when we plug this in, we're going to find that YCD is equal to 5.67 feet, and our Y from A to D would be equal to 8.67 feet by just adding the 3 feet. If we go back to our original picture there, remember the distance between D and B was equal to 3 feet. Oh wait, or was it 4 feet? Let me zoom out here. Oh no, it was 4 feet, right? So we found 5.67 from D to C. Let me label it on here and you all can fix it, right? We found this distance from there to there was 5.67. Well, we need to add 4 feet to get up to A right there because we wanted to find A to C. So it's actually 9.67 feet. 9.67 feet. Remember, these problems are all about options. It's about identifying all the options for FBDs. And then, it's not always, I think it's obvious to identify all the options, but don't skip options and think like, oh, well, that's not a good one. Or don't skip equations. Once you get the FBD, look at the equations. Also, look at all 3 of those equations. In this one, this last FBD that we were looking at, why not look at moment about C, then look at moment about D, and just, identify all those options and say, okay, how many unknowns would that have? Could it work? And then don't forget about sum of forces in the X and sum of forces in the Y. There's going to be problems that you run into where all of a sudden it's like, oh my gosh, sum of forces in the X has only one unknown, or sum of forces in the Y only has one unknown for this particular FBD. So really focus on these as options, identifying those options, being able to identify those options, and then just taking it one step at a time. You're going to find that that's going to be the most effective approach for these problems. Okay. And I see Morgan was telling me it was 4 feet. Okay. All right. Let's take a look at another example. We are not going to have time to go through this, but I wanted to get it started. And this is up on Canvas under the supplementary example problems. It's the first one. The very first class example, number 1, with discrete loads. So this one, we're basically asked to do the same kind of thing that we did in the last one. And so we have DC is equal to 4 meters right here. And let's go ahead and let's draw our given information here. So point, we're going to be given in this problem, we're going to have point A is about there, make point B right there. Point C is higher than B, but lower than A. So I'll put it right there. Point D is, can't really tell where it is relative to A. I'm going to go ahead and make it higher than A. And don't make any assumptions on these, right? If they don't specifically tell you that a point is, in line with another point, then we can't make that assumption. So I'm just going to put point D right there. And then I'll put point E, maybe about right. Where's point? It's bare. I want to make sure that this line right there, that this line is steeper. Okay, so that works. Those two lines are steeper than one another. This line is barely steeper. And then we have this one right there. So and then they're showing a pin support. I'm going to do it on a wall instead of on a floor. Doesn't matter because these are all 2 force members. And then we're going to have a 1.2 kilonewtons. We'll have a 0.8 kilonewtons and another 1.2 kilonewtons right there. We are given some geometry here. All of our horizontal distances are 4 meters. So even though maybe my picture doesn't look like they're all 4 meters, they are all 4 meters. So 4m, 4m. See, they do tell us that the vertical distance between the supports is equal to 3 meters. And they tell us that this distance at C is 4 meters. They do not give us D to B is unknown. Sometimes you'll see them call it D, a distance. Sometimes you'll see them call it a Y. It's the same thing. We called it a Y in the last case, but now these are D's in this case. And then so we have A, B, C, D, and point E. We are asked to find in this problem max tension and also dB and dd. Now, in this one, we don't know the slope of any segment. We don't know the slope of A to B. We don't know the slope of B to C. We don't know the slope of C to D, and we don't know the slope of D to E. When we start going through our options, you're going to find there is not a single FBD that only has 3 unknowns. When that happens, we have to look for more than one FBD to start solving the problem. So we'll get some equations from one FBD, and then we need to do a second FBD to get more equations and to be able to solve for some of those unknowns. But our process is effectively the same, where we just look through those options and start looking at, okay, for this option here, what equations can I get? From this option here, what equations can I get? So we'll talk about this a little bit next time, but it is also up on Canvas under those supplementary example problems. So they go through the full solution on Canvas if you want to take a look at that, because you do have this instance in your homework where you don't know the slope of any segment. If you have a known slope of a segment, you can do what we did on the first problem today. But if you don't have a known slope, it's going to take 2 FBDs before we can start finding a number and solving for those unknowns. You all have a great rest